Hi, my name is Dante and today I present to you the combined nonlinear and linearized envelope following circuit analysis method, or CNL-EF for short. This method was developed by me, Dante Regiani Freitas, and Professor Eduardo Gonçalves de Lima at the Group of Integrated Circuits and Systems from Universidade Federal do Paraná, with the financial support provided by the National Council for Scientific and Technological Development, CNPq, under the program PBT UFPR 2020. In this presentation, we'll be seeing the following content. First, an introduction to the area of circuit simulation, showing its importance and challenges. Then we'll see a couple current circuit analysis methods, which are the shooting method and envelope following. After, I'm going to present our proposed method, the CNL-EF, and I'll finish with the results and conclusions, showing how the CNL-EF compares to current methods, its limitations, and its benefits. Throughout the 20th century, we've seen a big explosion in the development of electronics. This was linked with the development of computational simulation techniques for the development of those electronics. So much so that today it's not possible to make electronics without previous simulation. One of the main difficulties with computer simulation is the limited computational power. As circuits get more and more complex, like in the telecommunications field, the needed computational power increases, and so it's necessary to make some compromises. For each situation, a different approach must be taken, that is, different compromises are chosen. Currently, there are two main branches to circuit simulation. Large signal analysis methods, which are used when a circuit has only periodic stimuli. An example would be the shooting method. And envelope following methods, which are used when a circuit has non-periodic stimuli. Usually those are composed of a carrier signal with a frequency in the gigahertz range modulated by a complex envelope with the frequencies in the megahertz range. For instance, the envelope following method. Our work proposes a solution for simulating non-periodic circuits similar to Moura and Lima's work. Reference number 2 focuses on the frequency response by using a modified circuit envelope method, whereas we propose a method for temporal analysis based on the envelope following method. So let's take a look into current analysis methods. First, the shooting method, mentioned previously. It consists in guessing the initial value for a transient analysis until the steady state is achieved. I said before, the SM is for periodic circuits only, so simulating a single period is enough. The steady state condition is achieved once the initial and final values of the state variables are equal. This is verified by equation 1. The diagram on the right side shows how it works. An initial guess is taken, then a transient analysis is ran, and it tests whether V0, the initial value, and Vt, the final value, are equal. If not, it takes the final value of the transient analysis as the new initial guess and runs another transient analysis. This repeats until equation 1 is true. Based on the shooting method, the envelope following is capable of simulating circuits with non-periodic stimuli. It does so by running new transient analysis after C periods have passed. The in-betweens are filled using equations 2 and 3, which replicate the results of the previous transient analysis. Once the established final instant of time is reached, the simulation ends, as can be seen by the diagram on the right. And now the proposed method, the combined nonlinear and linearized envelope following. The CNL-EF uses two envelope following analyses, one nonlinearized for large signals and a linearized for small signals. After both simulations run in parallel, they are added together, following the superposition theorem. The linearization is done by modifying all nonlinear dependent sources using equations 4 and 5, where f is the nonlinear function of the dependent source, flin is the linearized function of f, v is the circuit variable which the source is dependent on, and gm is a dynamic variable given by 5. We can better visualize how it works with the diagram on the right. So first, it takes the initial values, then runs both transient analysis, fills in the betweens, and repeats the process until the final instant of time is reached. Then it adds each component and gives out the result. Now let's see the results of the proposed method and compare it to a common envelope following analysis without linearization. To test the method, the circuit on the right was used, where R1 equals 1 kilo ohm, RL equals 50 ohms, C1 equals 10 picofarads, and C2 equals 1 microfarad. The current source F is dependent on the voltage given by Vs according to the equation 6, where I set equals 0.1 amperes, V set equals 1.8 volts, and S equals 5. The independent source Vs has a large signal component with a frequency of 1 GHz and a small signal component of 2 GHz. Both are composed of sine and cosine waves. And in equation 3 for the envelope following analysis, the time step was chosen to be 10 picoseconds, respecting the Nyquist criterion, and the number of periods between each transient analysis C was chosen to be 10. To run the simulations, it was used Python 3.9.0 with the libraries NumPy, SciPy, and Matplotlib. To establish a difference between small signals and large signals, a variable m was set to multiply the small signals component. When using an m equal to 0.25, the simulation presents a mean square error MSE of 0.00015 volts squared in comparison to a single EF without linearization. This is shown on the left. But when using an m equal to 1.25, the MSE increased to 0.00099 volts squared, shown on the right. This exemplifies how this method only works if small signals are valid for the independent sources. The proposed method accomplished the set objective to simulate non-periodic circuit responses. By testing it under different conditions, it was shown how the linearization can only be applied in small signals. Also, CNLEF can accurately reproduce results from other circuit analysis methods, such as EF, in the specified conditions with an MSE of 0.00015 volts squared, and with the benefit of being capable of applying linear analysis techniques. Finally, we'd like to acknowledge the financial support provided by the National Council for Scientific and Technological Development, CNPq, under the program PBG UFPR 2020. Thank you, and thanks everyone for watching.